Okay, so there's handouts working their way back. If you don't get any, there's more up front. Slide these back. Okay, so today we are talking about resistive circuits. For those of you who already started the lab, I guess those of you who were in the Tuesday session, or was there a session this morning? A lab session? Yeah. So you already got some exposure to the kinds of things we're going to talk about. For better or worse, the lab actually tends to run a little ahead of the lecture. That's just the nature of how the scheduling works out. So what are we going to do today and the next class? We are going to start talking about very simple circuits. Circuits that essentially contain two types of elements. They will contain some sort of source, a voltage source, a current source, or the like, and they will contain one or more resistors. And we will figure out how to analyze circuits based on those sorts of schemes. We will come up with some ground rules that we'll use in determining how circuits work, and that's the starting point. There is a homework online as of this morning, and that homework covers material from the first section and from this section as well. Okay, and it's due a week from today in class. Now, what does that mean? That means that you can turn in homeworks for the first 10 minutes of class. Once I start, which means I'll wait till 4:10. Once I start teaching, I will not accept any more homeworks. Okay? If you are worried about walking in late or something like that, you're welcome to swing by my office and turn in the homework earlier. I do not accept late homeworks. Okay? And late is even 2 minutes late. I'm not accepting it. Okay? Because otherwise I know what happens. Everybody starts showing up later and later, especially as you get busier in your other classes. You basically say, oh, I'll do that homework in the 1.5 hours I have while he's teaching, and then I'll turn it in when he's done. So we're not going to do that, okay? So it's due at the start of class, or you can turn it in ahead of time. You're welcome to do so. Just swing by my office and drop it off. It's pretty easy. It's not too long. Shouldn't take you too long. It's very similar to the material that the TAs are going to cover in this discussion this week. Yes, question? So you're somewhere behind your office? Yeah, slide it under the door. That's fine. If I'm not in my office, slide it under the door. That's fine. Okay, so we are going to start by discussing something called Ohm's law. In very simple terms, Ohm's law says that the voltage across a resistor is proportional to the current. In other words, V is proportional to I. That's what Ohm's law says. And in fact, the way we usually write that is we write V is equal to a proportionality constant called R, which I'll explain in a minute, times I. And R is a proportionality constant, which is called resistance. How many of you have learned about Ohm's law before? Virtually all of you. Okay. Have any of you ever thought it's kind of odd that Ohm's law actually works? Probably not. You sort of, by default, we tend to assume linear things make sense. But in fact, I'll talk about this in a couple of minutes. The fact that Ohm's law works is sort of unusual. And in fact, for most systems, Ohm's law only works over a relatively limited range. So some of you are taking the lab, and you've taken those resistors, potentially, and maybe you've looked at the resistor value and you've measured it, and you know what a resistor is anyway. If I take a resistor and I measure its voltage versus current characteristics, generally, for the range I'm likely to measure it in, it'll be linear. So that's good. That says, hey, that's Ohm's law. Voltage is proportional to current. Current is proportional to voltage, means I should get a straight line, which I do. But in fact, for virtually every material that we use, there is some range in which it becomes nonlinear. Typically what happens is it saturates. In other words, I will keep increasing my current, but my voltage won't change. Or in other words, as I keep increasing my voltage, my current will no longer be proportional. Okay? So for most components, there's a limited range over which Ohm's law works. But for the purposes of this class, fortunately, and in fact for most systems that we deal with, for most resistors that we're likely to deal with, we live in that range. So Ohm's law is not a true law in the sense that it's not a law that is universally applicable. It has numerous exceptions. It is only valid over a specific range, and it's only over that range that we get to use it. And based on that, we define a term called resistance. And resistance is the proportionality constant between voltage and current. More specifically, R is equal to V over I, where V is the voltage and I is the current, provided we are living in this relatively narrow range. And this range is quite wide for many resistors. So, broadly speaking, resistance is the ability to resist the flow of current or to impede the flow of electrical current. But resistance depends on many parameters. So let's think about this a little. Okay, so I will give you a box. And the box is made out of some resistive material that you know. Anybody know those resistors that you've been using in the lab or that you've seen around? What are they made of? The outside is ceramic. The inside is typically not ceramic. The ceramic resistors are actually pretty expensive. Sorry? Graphite. Yeah, it's actually carbon. Yeah. So it could be amorphous carbon or graphite or a mixture of the two. Okay, they're typically carbon. Better quality resistors, like resistors that are used in good quality audio amplifiers, are made out of metal. They're called metal film resistors, which are layers of metal and ceramic. But resistors are generally made out of a material with known electrical quality that we can then use to define a resistance. Okay, I'm going to give you two pieces of the same material. The material is identical. Okay, it's some sort of carbon, but it's identical in properties. And I'm going to tell you that I'll make one roughly half the length of the other. And I will tell you that this, if I were to measure the resistance from this side to this side, has a resistance of 1 ohm. What do you think the resistance of this one is? 2 ohms, okay, right? So you got 1 ohm there, 1 ohm there, so you said 2 ohms. Two questions. First, why did you say that? Okay, you know something that I haven't explained yet. It's in series. That's one way to look at it, yeah? Okay, you said it's proportional to the length. Okay, that's true. That is a characteristic of most resistive elements. The resistance is proportional to the length. Okay, so that's a good answer. Did you make any assumptions? This is harder. Were there any assumptions underlying that statement that you just made? Anybody see anything? And I'm going to give you a hint. Think about the contacts. Yeah.
Not so sure, but like from the end point.
Uh-huh.
At that point, like the area doesn't really matter so much.
You mean right at the corner?
At the end, yeah.
Uh-huh. Yeah, this is harder. This is not so obvious. Okay, this is a difficult question, but you're kind of on the right track. Anybody? No. It's yeah. That's right. Now you're getting there. The point is, the assumption, when I said going from this to double this was multiplying by 2, assumed that all the resistance in my measurement came from this box, and there's no resistance associated with the contacts. Because think about, let's pretend the contact contributes 0.1 ohms. Okay? Let's pretend. Then this would be 0.1, this is 0.1, what's left in the box? 0.8. What about here? I have 0.1, I have 0.1, I have 0.8 and 0.8. What should that give me? 1.8. Okay? So you see, we made an assumption there. It turns out it's a really good assumption. But we did make an assumption. I'm glad you made that assumption, but I want you to be aware that it is an assumption all said and done. One of the assumptions we tend to make, and you will make almost universally in all the work that you do in this class, is the resistance of the wires, etc. doesn't matter. So when I tell you the resistor has a resistance of 1 ohm, I can ignore everything else. Okay, having said that, so we've talked about the effect of length. There's another effect, that of width. If I connect something that's twice as wide, but it's the same material, well, now there's essentially more paths for the current to flow. Here the current was flowing this way. Here the current has more space over which it can flow. So I would expect then this to be less resistive. Okay? Now we get to define a property, and the property we get to define is resistivity. And resistivity is a property that describes in a unit cube of material what is the resistance. Okay? And then all you do is, if you know what the unit cube resistance is, if you want to find the resistance of something that's not a unit cube, you just multiply by the length, because the length increases resistance, and you divide by the area reduces resistance. Let's draw that again so it becomes a little clearer. And I'm going to do this in 3D, or do my best to do it in 3D, so that we can see this. Okay, so this is one cube, and this cube has a resistance of 1 ohm. If I were to connect another cube to it end to end, now I've got two cubes in series with each other, and these together give me a resistance of 2 ohms. Because the current has to go through this cube, which contributes 1 ohm, and it has to go through this cube, which contributes an additional ohm. Okay, that's why intuitively saying they are in series makes sense to you. All right, but now let's change it. I have one cube, and I will put another cube in parallel with it. So I've got current going this way, current coming out that way. Now the current can go through both of these cubes at the same time. They're in parallel with each other. So it's like having a wider road. There's more space. You actually get a lower resistance. So that's why we end up with this rule, which says the resistance of a rectangular structure, this is calculated for a rectangular structure, is equal to rho, the resistivity, times L over A. Okay, what do you think the units are of resistivity? You can get it right from that equation. What are the units of resistivity? Yeah. Not per square, you're getting close. Yeah, it's ohm length, ohm meter or ohm cm. Okay? Because remember, you're multiplying by length to the 1 and you're dividing by length to the 2, which means this has to be in units of ohm times length, such that the final answer comes out in ohms. Okay? Okay, good. So that's how we define resistivity. This equation will also work for a non-rectangular structure, provided it's a linear structure. For example, if it's a cylinder. If it's a cylinder, as long as you know the length of the cylinder and the area of the cylinder, this still works. Okay? If you get to more complicated shapes, it's not so easy, but fortunately everything we're dealing with is relatively simple structures. So that's resistivity. We talked about conductance and resistance in the last class, and we said the unit of conductance was either Siemens or mho. Correspondingly, there is another unit that is the inverse of resistivity, and that is conductivity. Okay? And conductivity, which is written as sigma, so that's rho, that's sigma. The relationship of resistance to conductivity is just R is equal to L divided by A divided by sigma. Sorry? This is not Q, this is sigma. We haven't talked about charge. Q. Charge density. I'm sorry, what do you? Q over A. No, that's not related to sigma per se. Okay, we'll talk about charge later. Okay, the units of, so let's think about it. What are the units of sigma? 1 over ohm cm, right? What is 1 over ohm? Siemen or mho, right? So it is Siemens or mhos per centimeter. Okay? Break that up into its fundamental units, and you can figure out. Okay, so we've got rho, I'm sorry, we have rho and we have sigma. So that's how we calculate the value of a resistor. Okay, now let's take an example. Those carbon film resistors that you were working with, let's say I give you 2 resistors. They're nominally identical. All those resistors you were dealing with in class were nominally about the same size, right? How do we vary the resistance? If they're about the same length and they're about the same diameter, how do we vary the resistance? Sorry? Well, but to do that, it would make it longer, right? If I was putting material in series, wouldn't it make that resistor longer? Okay, so I want to keep the resistor the same size. Sorry? Use a different material. That's the right answer. That's actually what they do. So when they make these carbon films, to vary the resistance by a small amount, they just change the dimensions. In fact, if you open up one of those resistors, for really high resistances, it'll actually be a little serpentine. Okay? It won't be a straight line. It'll be sort of really squiggly. But if they want to have big change in resistance, they just change the material. This value, rho, or this value, sigma, tends to be a property of the material. Okay, now let's talk. In the very first class, I asked you about conductors and semiconductors and insulators. Today we're just going to talk about conductors and insulators. All right, based on these terms that I have provided for you, can you give me a one-sentence definition of the difference between a conductor and an insulator? So give me a definition of a conductor and contrast that to a definition of an insulator. Yeah?
A conductor would have low resistivity.
Good.
What's the other word?
An insulator?
An insulator would have high.
Perfect. A perfectly good way of saying it. A conductor would have low resistivity and an insulator would have high resistivity. If I asked you to say the same thing in terms of conductivity, sigma, you would say the opposite. A conductor will have high conductivity, a resistor will have low conductivity. I apologize, an insulator will have low conductivity. That's right. So conductors, resistors, etc., those are properties, they're described materials, and the property that describes them, that quantifies them, is resistivity or conductivity. Okay, how many of you have heard of superconductors? Okay, can you define a superconductor for me in terms of these units? Yeah. Yes, it has a resistivity approaching 0. In an ideal world, we can treat it as being 0. Okay, anybody know? Why do we care about superconductors? Yeah? Very good. One reason is they're useful for transferring power without loss. Can you name an application for which we actually use superconductors on a regular basis? Yeah?
Large magnets.
Large magnets. Can you explain?
So for large magnets, you need large amounts of currents.
Mm-hmm.
And if you have a lot of resistance, you can have superheating. So you use MRIs.
Perfect. Okay, very good. So for large magnets, and he actually came to the question I was about to ask. I was going to ask the application, and he gave it to me, which is MRIs. So anything that you need a large magnet for. An MRI, for example, which is magnetic resonance imaging, is a system that uses a relatively large magnet. It's actually an electromagnet, which has a really large coil. And if you were to unwind the coil, it would be this wire that would be miles long. And the resistance adds up, right? Because it's a really long wire. And if you've got this wire miles long and you're flowing current through it, it loses power and it causes heating for reasons that we'll see in a minute. So that's not so good. So one of the applications of superconductors is for large magnets in systems such as MRIs, where we can essentially reduce the power loss through heating. Okay? And that's one big advantage of superconductors, and that is what they are used for. We have several of them on campus used for specific analytical chemistry systems. Okay, any other applications for superconductors that you're aware of? Yeah? Yeah, that's true. It's but for the same idea. Yeah, okay. Anything else? Anything in transportation? Not monorails per se, specific, yeah. Maglev trains, magnetic levitation trains. Do you know why they use superconductors there? The underlying reason is actually the same as the large coils. Because you've got these tracks that have to run long distances, it allows you to have a loop of current flowing without significant loss. Okay? There's current flowing through this track. The track's really long. If it had resistance, you'd have losses, and then that causes issues. That's the underlying reason. Okay? Yeah?
Is there like a fundamental physical difference between a superconductor and a conductor, or is it just like a certain line and you say, oh, now this is superconductor?
So that's a good question. Is there a fundamental difference between a superconductor and a conductor? There is in the way we model it for the following reason. It turns out if we'd have to get into the underlying reason for why resistance exists. I mean, why does something have resistance? Why does current not just flow without a problem? Let's talk about that. Anybody know? Why does resistance exist? Yeah.
Because the nuclei is so slow that they wouldn't collide with electrons passing by, so electrons pass.
Okay, you're getting to the underlying reason. Yeah.
In metals versus ceramics, there are different reasons, but in metals it's because you form Cooper pairs.
Okay, all right, good. Let's put it this way. Okay, let's break it. You have an electron trying to get through this wire. The electron interacts with everything in the wire. What does it interact with? What's in the wire? There's nuclei, and there are the electrons. It turns out the electrons interact with both of them. They interact with the nuclei, and they interact with the electrons in different ways, depending on the material. Some cases, there's strong interactions with the nuclei, in other cases, not so strong. Those interactions mean I have an electron sitting over here, and this electron is trying to go by it, because the current wants to go that way, and it's swinging this way. What happens to this electron? It's swinging by right here. What is it going to do? Is it going to go straight? Is it going to go up? Or is it going to go down? Electron, electron. It'll probably get pushed up because it gets deviated away from this electron. They're repelling each other, right? The two electrons repel each other. So similarly with a nucleus, it'll get pulled down. So imagine you have this electron that's trying to go from here to here, but it's not able to do so. In fact, what happens is it sort of bounces around, and it's constantly scattered as it goes down the line. There are certain scattering mechanisms which are dominant, and in ceramics and metals, we have different scattering mechanisms that are dominant. It turns out, if you take certain systems and you order them just right by minimizing the vibration of the nuclei, so that means lowering them to very low temperatures, it turns out electrons are able to go through with dramatically reduced scattering, which means electrons essentially go like that instead of bouncing all over the place. And that is how we classify the difference between superconductors at a high level. That's how we classify the difference between superconductors and conductors. Yes?
Do the electrons leave back from the material? I mean, not from the other end.
Yeah, you mean out here? Okay, that's a good question. Conceptually, the answer is yes. But it turns out, now most of you have taken or placed out of high school chemistry or freshman chemistry? Freshman chemistry? Yeah, have you heard of something called work function? Yeah, you have. You may not remember, but you've heard of something called work function. So it turns out, if you have an electron in this system, it takes, let's say it's aluminum, for example. It takes about 4 electron volts to get the electron to go out that way. So it would have to be a really high energy electron. It is conceptually possible, but in practice, unless you have really high voltages on the system, you get no electrons coming out. Okay? Question? Mm-hmm.
Does it matter where the connection points are? Because when the areas are when the resistances are much wider than the wires, then does it matter where?
Yes. Good question. So the point is, let's say I just had a little point contact over here connecting to this really wide resistor. Does the position of the point contact matter? Absolutely. And that leads to something called contact resistance, which we are going to completely ignore in this class. Okay? But yes, it does matter, very much. Yeah? Mm-hmm.
So the follow-up to my first question, the reason it's easier for the electron to go out the other end is because it's heading in that direction already, right?
No, that is one reason, but that's sort of underlying. That's a consequence, really, not a reason. The reason it's easier for the electron to go from here and exit here is the energy required to exit here. Because this contact is a good contact, it doesn't need that 4 eV it would require to exit here. In fact, what defines a good contact, it turns out, is something that doesn't need much energy to leave. So that's how we make good contacts. Yes? Correct. That's right. In fact, the electron is not, remember, as we said in the very first class, the electron is not actually, it's not the same electron going all the way through. It's just transferring energy down the line. Okay? But conceptually, it doesn't change the idea that we're using here. Okay? Yeah. Uh-huh.
If you have a wire like this, or
like this?
yeah,
Mm-hmm.
and there's two contacts. If you bend the resistor and the contacts are almost next to each other,
Uh-huh.
will the electrons go through the wire like the loop form?
Uh-huh.
Or will they go jump through the air?
Okay. Good question. We have that tubular resistor, and I bend it such that it's like this, and I have two wires right here. Okay? And the question he asked is, would the electrons actually go all the way around, or would they maybe just jump? The answer is, it depends on how close they are. For the purposes of this class, you would say they will always go all the way through the wire. They would never jump. But it turns out if you get them close enough, they can actually jump. And there's it's a quantum mechanical process called tunneling, which we're not going to talk about in this class. Turns out, by the way, at low voltages, you'll have to get them within about 2 to 3 nanometers off each other. But we do that. It turns out your modern microprocessors, actually the wire on the top of the transistor and the bottom of the transistor are close enough that some fraction of electrons actually jump. We use that for something that all of you own lots of. You all own lots of flash memory. Today, I believe there's like 1 million flash memory transistors per person on Earth, something like that. Okay? So all of you own flash memory. The way you program flash memory is by using that jumping, it turns out. Okay? So every time you put a song on your MP3 player, that's exactly what you're doing. You're making little electrons jump between two wires. Okay? Okay, so that's the general idea of Ohm's law. In this class, we're going to assume that it applies across the board when we talk about resistors. But let's spend a minute thinking about why Ohm's law actually works. Okay? Think about what current is. So current depends on, we talked about this earlier. What does current depend on? Current depends on the number of electrons, and it depends on how fast they're moving. Right? But we would expect the speed to have a quadratic relationship with voltage, because speed is quadratically related to kinetic energy, and voltage is a potential energy measure. So I would expect a quadratic relationship between the velocity of electrons and voltage. By default, that's what I would expect, because you know that voltage is a measure of energy, right? It's potential energy, in fact. You know velocity is quadratically related. It's the square root, or it's proportional to the square root of energy, right? Because kinetic energy is related to velocity squared. So you would expect then by default, any parameter that depends on velocity should have a quadratic relationship with voltage. Well, current is proportional to velocity. So then by default, I would expect a quadratic relationship between current and voltage. In fact, we don't get that. We get a linear relationship. Yeah?
You said that current's proportional to the velocity, but in practice, when you increase current, you're not really changing the velocity of electrons, you're just changing the number of carriers?
No, actually that's not true. It depends on the system. In some cases, you are changing the number of carriers. In other cases, you are changing the velocity. But in fact, the velocity only is linear, only goes up over a limited regime. It ultimately maxes out. Okay? But in fact, for most systems that you deal with, you're not changing the number of carriers. You are increasing the velocity, because our velocities are generally, in the scheme of things, not that high. Okay, so let's think about why that happens. Why is it linear? Okay? Now, it turns out It's because of the idea of conduction that we talked about earlier. We don't have a single electron going all the way through. What we do have is an ensemble of lots of electrons bouncing around and interacting with each other. And because of these bouncing arounds, let's say I have an electron and there's a nucleus right here. This electron comes here. What does it do? It accelerates as it approaches a nucleus, right? Nucleus is positive, electron is negative, it's going to accelerate. If I have one electron here and another electron here, and the electrons are coming together, what happens to the velocity of this electron? It slows down. So the velocities are constantly changing. It turns out if you average the ensemble of all of these electrons with all their different velocities, etc., and you do an ensemble calculation over the entire number of millions or billions of electrons in your system, you will end up finding that because of the averaging effect, the square behavior goes away and you end up with linear behavior. Okay? If you had a single electron and the electron was not perturbed, the velocity would indeed show a quadratic form, and therefore the current would show a quadratic form. But in any situation you deal with, at least in this class, we never have that situation. We always have millions or billions or trillions of electrons, and all we're dealing with is the ensemble effect, and none of them move through without stopping and starting and stopping and starting. Okay? So that's just a side note. I don't know if it's ever bothered you as to why Ohm's law actually even exists as a law. It's one of those things that, you know, used to keep me up at night. So it's nice to know that there's an actual reason for it. Okay, let's take some examples. Let's take some examples of materials that we actually deal with. So here I have a list of conductors, semiconductors, and insulators. Okay? I'm going to challenge this list in a minute. But you can see, if I look at the numbers, so typical conductors that we deal with are metals. Okay? Not all metals are good conductors, but most metals tend to be reasonable conductors. And you can see that they have really low resistances. Their resistivities are in the order of 10 to the minus 8. Compared to an insulator. An important insulator might be polystyrene or Teflon, glass as well. And you see, these have resistances which are 10 or 20 orders of magnitude higher. Okay? The resistivity of glass, for example, is 10 to the 12. The resistivity of copper is 10 to the minus 8. Huge difference. Orders of magnitude difference in resistivity. Okay. Semiconductors tend to be somewhere in between. They tend to be sort of halfway between, not really halfway, but in somewhere in the middle between conductors and insulators. Okay, let's take a side trip for a minute. Does anybody know? So carbon is, on this list, it appears to be a semiconductor. Okay? Is it always a semiconductor? Can you give me an example of carbon that is a conductor? Graphite, very good. If you were to take the pencil lead inside your pencils and you were to measure its conductivity, it would actually be really low. Not quite as low. Graphite and pencil lead is not that good quality, so it's not quite at this level, but graphite is actually a fairly good conductor. Anybody know what we use graphite for in electronics? Yeah?
Electrodes?
Yes, electrodes for what?
When you separate sodium chloride into sodium and...
Okay, good. It is used as electrodes in electrolysis. That's true. Okay. It is also used, it turns out, graphite or amorphous carbon mixed with graphite is used as electrodes in motors, in some motors. Okay, because it's nice and smooth. And so when the motor is turning, the electrode rubbing against it, it doesn't wear out. It lasts a long time. Okay, so we've talked about a version of carbon that is a conductor. That was graphite. Okay? Graphite is also, depending on its quality, can be a semiconductor. Okay? If it's more amorphous, it actually tends to be a semiconductor. Can you give me an example of carbon that is essentially normally treated as an insulator? Diamond, that's true. Diamond, at room temperature anyway, diamond is essentially an insulator. It's not as good an insulator as these, but it's a pretty good insulator. Turns out diamonds actually has been a reasonably active area of research in the semiconductor field for decades. Anybody know why? What's interesting about diamond? Yeah.
When you generate electron-hole pairs, it conducts much better.
That's true. The conductivity of diamond depends very strongly on how many electrons are in the system. And that means it's actually a semiconductor. That's fundamentally what you're saying. Any other reasons? There's something really unique about diamond as an insulator, which is remarkably unique. And it's too bad diamond is kind of expensive, because otherwise we could use it for really cool things. Yeah. That's true, but there are other good crystals as well. Quartz is a good crystal. So it's not the fact that it's crystalline that's interesting, yeah? Yes, it's a very good thermal conductor. It turns out most, and that, by the way, is related to the comment you made earlier. Most insulators, electrical insulators, are horrible thermal conductors. This is good and bad. The plastic you coat your wires with, it's a bad thermal conductor. So it's also a bad electrical conductor, but if the wire gets hot, there's no way for the heat to escape. That's good because when you touch the wire, it doesn't burn you. But it's bad because the heat keeps building up until the thing actually catches fire. That's actually kind of a problem. Yeah, question? What's that? Okay, that's a good question. Well, can you bend diamond? Yeah, we'll talk about thin film diamond in a second, okay? I'll address that. So, diamond is unique among insulators in that it is a reasonably good insulator, but is an excellent thermal conductor. So, if I could use diamond to coat all my wires, I wouldn't have to worry about them heating up. The heat would dissipate. It's not so important for wires, but for certain applications in semiconductors, that would be really useful. Now, getting to his point, well, how do you put diamond? I mean, diamond's this big brittle thing. How do you put it down such that you could bend it? It turns out thin film diamond, if you can do it, there are ways to deposit it. All the really cool ways of depositing it, turns out, were invented by the Russians, actually the Soviets, back in the days of the Soviet Union. It turns out you can deposit it, and if it's thin enough, it can actually flex. Okay? Mica is an example of a crystal. If it's thick, it's really brittle, and you cannot flex it. But if it's thin, it turns out it flexes really nicely. Okay, but the problem with diamond is it tends to be expensive. Anybody know why diamond as we use it today is really expensive? Yeah. Yes, it's not really expensive. It is not really rare. De Beers just buys up all the diamond on the market that it can. This is a fact, and De Beers will now tell you it's true. It is an artificially controlled market. If you were to go discover a new load of diamond, De Beers would immediately come and buy it all from you because they don't want you to put it on the market because that lowers the cost of diamond. So diamond is actually not that expensive. Diamond is expensive because De Beers figured out that it's kind of nice looking, and if you control the market, people will pay ridiculous amounts for something that really isn't that expensive. Okay? Now, here's the really beautiful story. There's this bunch of guys from Siberia, okay, who figured out how to put coal and a few other things, a few other impurities, inside this high-pressure, high-temperature chamber and press it hard enough, and it actually becomes diamond. So it turns out today you can get really good synthetic diamonds, and these guys, they moved from Siberia to Florida. That was probably a good choice, right? I mean, and they've set up a factory in Florida, I don't know exactly where, that's actually starting to produce synthetic diamond. And because it's synthetic, they can give you diamond of whatever color you want. They can add in colors. They can add in little impurities into the diamond that change the color. And they actually use this. Not so relevant for EE42 or 100, but it is. Because it turns out, because of the availability of synthetic diamond, we are now starting to look at diamond for applications that we would not have looked at it for earlier. For example, huge investments have been made into diamond-based electronics by the US military. Can you guess which arms of the US, or which arm of the US military has made those investments? Actually, it's an unknown. It's an arm you probably don't know. It's kind of like the Air Force, but not exactly. It's MDA, Missile Defense Agency. Okay? Because they want to make smart missiles to knock out other missiles, and they want to put electronics in the missile. And diamond, because it conducts heat really well, turns out works really well as a semiconductor at high temperatures, they've actually put a lot of money. It's called the Missile Defense Agency. It is an agency that exists here. Most people don't know about it, but it's actually tasked with building missiles to knock out other missiles. Okay, so that's a quick side note on material properties. There are also some interesting applications that we should talk about. We often use resistors to make specific structures. For example, we make a specific resistor called a thermistor. A thermistor is a resistor that is specifically designed to have a resistance value that changes in a known way with temperature. We generally want it to be relatively linear, and you can make thermistors using materials where the resistance will change roughly linearly with temperature. The advantage then is you can use that as a sensing element in a digital thermometer. Okay, so that's one example. A piezo resistor is a resistor whose resistance changes with mechanical deformation. We actually talked about that in the first class when we talked about Rochelle salt. Okay, so that's a piezo resistor. Two elements that you will deal with in the labs, for those of you who are in the labs, are so-called rheostats and potentiometers. These are devices that have variable resistance. Now, how do we make one of these? Let's think about how we would make a variable resistor. And I'm going to give you a hint. It actually looks a lot like this. Here's what we do. We take this resistor and we put a little probe that can touch at any point. And we bring this out as the wire. So one wire would be this side, and the length of the resistor depends on where we position this probe. So it is essentially, it rotates, and depending on where its position is, it sets how much of the tubular system is actually part of the resistor. And so the way we show that is like this. A rheostat would be a two-terminal device, so we'll have a resistor with a probe, and you change the position of the probe to change the resistance. A potentiometer is a three-terminal device. You have access to both sides. You have access to this side and to this side, and again, it's a probe, and you can move it. You are going to use these in your labs. We use these to tune circuits. We use them to change the gain of amplifiers. The volume controls, or the old knob-style volume controls, in all of your electronic devices are, in fact, potentiometers. Yes, question?
So can the same resistor be, say, a thermistor and a rheostat, where it depends both on temperature and you can control how long it is?
Okay, so the answer to that question is fundamentally yes, and in fact, that's a bad thing. Turns out all resistors, their resistance depends on temperature. Okay? No, yeah, that's true, but the bigger problem is it's sort of non-linear. Okay? Resistance changes kind of in a non-linear way with temperature. So all resistors are, in fact, arguably thermistors. And you could make, therefore, every rheostat or potentiometer is, in fact, a thermistor as well. The problem is it's not linear. You're asking me, are there any specifically designed thermistors that have a potentiometer function as well? I'm not aware of one. It conceptually would not be impossible to do. I'm just not aware of one that exists. Okay? All right, any other questions? Yes?
So why would you have to coat this, going back to the diamond? Why would you have to coat the entire wire in diamonds? Couldn't you have like rubber and have diamonds or small pieces of diamond nested in it that would actually keep it?
Yes, that's a good idea. If I wanted to get the heat out, I could just have heat pipes that spread throughout. And in fact, there are people who are looking at diamond-based cooling that are doing exactly that. Yeah, so good idea. So, okay, so that's general idea of conductivity. Now, let's go to a concept I touched on when I talked about heating. It turns out that resistors, when you flow current through them, burn power. If you look at the units, power, what are the units of power? Watts. And we already know that power is, for an electrical system, is voltage times current, because the units work out. Watts is equal to volts times amps. Well, if it's going through a resistor, we know V is equal to IR. So we replace the V by IR, and then we see that the power through a resistor is I square R. This power, how is it dissipated? It is dissipated as heat. So anytime you flow current through a resistor, it heats up. And that heat comes from this equation, I square R, or equivalently V square upon R. Now, that can be good and bad. Can you give me some examples in your day-to-day lives of how we use this in a good way for things we want? Yes? Toaster, perfect example. A toaster oven is, in fact, a resistive heater. Okay? Any other examples? Yeah. Sorry? Hair straightener. That's probably true. To be honest, I've never opened up a hair straightener, but certainly I have opened up a hair dryer, and that has certainly got resistive heaters. Okay? Yes. So resistive heaters are good that way. Resistive heating is also bad. You guys gave me examples earlier when we were talking about superconductors of how heat generation in resistors is bad. Okay? Also, if you have you've probably experienced this at some point. You have an electronic device, and it suddenly you start smelling smoke, and then it just stops working. Why is that? Something in your device developed a hot spot. In other words, the resistance in some region went up for some reason. And we actually know why most of these things happen, but it's not really relevant. And they heat up, and then once it starts heating up, it gets hotter and hotter, and then ultimately it burns. So this is a problem. This is a cause of a lot of failures. Yeah, in fact, soldering irons, actually, we use a resistive heater. That's also how they work. Yep. Mm-hmm. Yes, light bulbs, old-style light bulbs that ideally you shouldn't be using, but apparently some people really cling to light bulbs. Okay, you probably know this. There's this weird fight to remove There's legislation in place that says you should use compact fluorescence, and there's people saying, oh no, nobody can take away my damn light bulb, right? I don't know. That's political. I'm not going to get into that. But it is, in fact, correct. A wire filament light bulb, the old style light bulbs, the incandescent light bulbs, use a wire filament. They heat up. And it turns out when they heat up hot enough, they glow. And you see the glow. Anybody know what percentage of the energy goes into heat versus goes into light? Yeah? Yeah, it's 3 to 5%, depending on the filament structure and how old the bulb is, goes into light. Yeah. Mm-hmm.
Is that what happens when a light bulb burns out?
Yes. Yeah, what happens is, well, it turns out what actually happens. So why does a light bulb burn out? When you are continuously flowing current through it, it's also heating up, and over time, the material on that filament starts evaporating. And so it gets thinner and thinner, and when it gets thinner, what happens to its resistance? It goes up. So it's now getting hotter and hotter at that point, and ultimately it just burns out completely. Yep. Mm-hmm. Why did we use tungsten? 2 reasons. Tungsten, it turns out, for the kinds of voltages we use, has about the right resistance to get hot enough. Okay? And 2, tungsten has really good high temperature capability. It can handle high temperatures really well without evaporating and burning out very quickly. That's why. But the first light bulbs were not tungsten filament light bulbs. Anybody know what they were? Yeah. Carbon filament light bulbs. It was really interesting. Actually, it turns out my granddad had a carbon filament light bulb in his house, and this was in the late 1990s. No, it was early 2000. Late 1990s, early 2000. It was from 1920, and it still worked. So the house is now gone. He passed away, and they sold it off. But I wanted that light bulb. So, okay. Okay, so that is one example of what is called Joule heating. It is called Joule heating. Any of these resistive I square R behaviors are referred to as Joule heating. And the reason for it is kind of dumb. It's because, the units of energy is joules. So we call it Joule heating. Okay? All right. Now, let's take another very important example. The big transmission lines that you see on, next to highways, etc., they are not running at 120 volts. they are typically running at multiple kilovolts. Depending on where you are and which country you're in, the voltages vary, but they're typically multiple kilovolts, 4 kilovolts or more. Okay? Why do we do that? If I do that, I have to put a transformer somewhere to bring the voltage down to 120 volts. Why do I transmit at higher voltage? Yes? Yep? That's right. That's exactly the right answer. Think about it. You don't care, okay? You say, I want to run my microwave oven and I need 1,000 watts. And my system, my voltage is getting delivered at 110 volts. So I don't care really what's going on elsewhere as long as it comes to me at 110 volts, so I can draw about 10 amps. That'll give me about 1,000 watts, right? So that's my goal. I have two choices. If my wires are running at low resistance from let's say my electricity comes from West Virginia, shows up here because there's a lot of coal in West Virginia, so it's traveling 3,000 odd, 2,000 odd miles from West Virginia to here, and that whole time it's traveling at 110 volts, which means it has to come to me at 10 amps. Okay? Well, I've got 10 amps going through a relatively low resistance wire, but the wire is the length of the United States. So I burn a lot of power in the wire. If, on the other hand, I come at, let's make it easy, let's make it 1,000 volts. If I come at 1,000 volts, how much current do I need to provide 1,000 watts? 1 amp. So I just come in at 1 amp, well, I square R got a lot smaller. It got 100 times smaller. So this is why we do it. So for these reasons, we generate power at higher voltages. In fact, we generate it at intermediate voltages, step it up to higher voltages, send it across the country at high voltages, and then step it down to low voltages for household use. Okay, so we've answered one part. We've explained why we use it at high voltages for transmission. Anybody know why we don't use high voltages at home? Yeah. Well, one is a safety concern, but if you're not an idiot, you don't go sticking your hand into a plug point, so what? Yeah. That's true, but think about it, it's more expensive to step it back down to a low voltage. It came in at a high voltage, we had to put a transformer and bring it down to a low voltage. Why not just leave it? Yeah.
Well, if you have it going from just one place, doesn't that mean that if you were to stop it in one place, you wouldn't be able to have voltage anywhere else?
No, that's not true. I mean, as provided, we'll talk about why that's the case when we talk about source impedance, okay? But fundamentally, that doesn't, you can still distribute it to multiple places, yeah? Actually, it is somewhat related to safety, but it's more related to insulators. All insulators, it turns out, have a certain field at which they stop being insulators and will become conductors. That's called the breakdown field. Okay? So you've seen this. When you buy your plastic-coated wires, your extension cables, they are rated for a particular voltage. That rating limit comes not from the wire itself, but from the insulation on the wire. If you put too high a voltage on this cheap insulation that we use, it's no longer an insulator. It actually becomes a conductor. Okay, for reasons that we won't talk about. So that's why. It allows us to use cheap insulation around the home. That's why we do it. Okay, so that's the conceptual idea. This is the same example that I gave earlier, but this is with slightly different units. So you can calculate the power draw. So let's say a house is dissipating 1.2 kilowatts. If it operates at 120 volts, it only needs 10 amps. Okay? But let's put some real numbers in it. Let's take a copper wire that has a 5 millimeter radius, half a centimeter radius. So it's a centimeter thick. That's a pretty thick wire. Okay? And it's 100 kilometers long. You calculate its resistance. So we've got rho times L divided by A. Since it's tubular, it's pi r squared. Works out to be 22 ohms. Look at that. The power lost transmitting 100 kilometers at 120 volts was 2.2 kilowatts. We actually lost more power than we needed. That's why we run at high voltages. We run at high voltages so this number stays low because I is low. That's why we do it. Okay. Yes?
Is there a reason as to what number we chose to step it up to?
Yes. So the question is, how did we pick the numbers that we picked? There's actually not a single number. There's multiple voltage transmission levels. Okay. Locally, we transmitted 440 volts. Long distance transmission is often at 4.4 kilovolts. There's also some 2.2 kilovolt transmission. We pick numbers that are easy multiples of each other because it's easy to set up transformers that can step them up and down. Okay? The origin of 110 volts is actually more historical than fundamentally technical. Okay? There's no, it's more just, that's what we started with, and so we've kind of lived with it. Okay. So we do the same math for a high voltage line, and we do it for a high voltage line here that's running at 100 kilovolts as opposed to 100 volts. Okay, so this is a long distance transmission line. And now we see that the same loss is only 3 milliwatts. So we've gone from, what did I say, 2.2 kilowatts to a few milliwatts. And that's why we do it. What's the disadvantage of transmitting at high voltages? Yeah.
Oh, I was going to say, like, for very high voltages, they see other problems, like radiation.
Yes, well, yes, I agree. The evidence is moderately clear. I wouldn't say it's 100% clear, but it is moderately clear that there is radiation from high voltage lines, and there appear to be some correlations between living near high voltage lines and cancer. Okay, the evidence is not 100% clear. Okay. Yeah, cancer is bad too. That's true. Yeah, yeah. Yeah, and that's again related to cancer or distortion. Your cell phones often don't work well when you're close to a high voltage line. If you drive down I-5 going to LA, you'll find there'll be spots where it'll drop out, and that's because there's a high voltage transmission line down there. Yep. Hmm? I-load? Oh, just because I was specifying that that is the current needed by the load. Okay? Whenever you see me write something like this, well, I'll say I load or I V1. That is the current required by the load or the current required by V1. That's just the way we specify. Okay. Any other problems with running at high voltage? You need transformers. Transformers are expensive, and there are losses in transformers, and every now and then, on a fairly regular basis, actually, they explode. Okay? You've seen this happen. You've probably heard it. You'll hear boom somewhere, and then you'll lose power. That happens pretty often. It's surprising how often transformers explode. So that's kind of a problem. There are movements in place within the US to develop new grids that will perhaps be efficient, but maybe we don't need such expensive transformers, or trying to figure things out. So changes will happen in your lifetime, I would predict. Okay. All right. That's it. So we've talked about intro to resistors. We are now ready to start talking about actual circuits. So I'm going to show you an arbitrary circuit here. I promise we are not going to analyze this circuit today. Okay? But I'm going to define some terms. Some terms that you're going to hear me use throughout this course. First, the first term I'm going to define is what I will call a branch. Okay? And a branch is, for our purposes, just a single element. Okay? So for example, R4 here, it's a resistor. It's a branch. Okay? The next element I'm going to define is called a node. And for example, that might be a node, this might be a node, this might be a node. And a node is a connection between two or more branches. So, N6 over here is a node because it's a connection between R3 and R4. N2 is a node because it's a connection between R3, R1, R2, and L. So we've now defined two terms. So but you've seen that nodes can be two or more elements. Really, doing math on this node, it turns out, is trivial. So it doesn't really help us to worry about this. So we, in fact, typically define a specific type of node where the math is more complicated. And that is called an extraordinary node. And that is a node that's a connection between at least 3 branches. Maybe 4, maybe 5, but at least 3. So N6 is not an extraordinary node. N2 is an extraordinary node because you can see it as 4 branches. Okay. And the final term that I'm going to need as we start doing analysis is loop. And a loop is exactly what you would think it is. It is something that's a closed path. And by closed path, I mean I can start at a point, go all the way through the circuit, and I will end back up at that same point. So I can close it. So this is a loop. Okay? This would be an example of a loop. Can you give me an example of a loop that involves R4? Yeah, the bigger one. Okay? That's a basic term. So you've heard loop, node, extraordinary node, and branch. We are now going to start defining some rules for circuit analysis. First, for any circuits that you are likely to deal with in this class, it's usually possible to redraw the circuit such that we don't have to have lines crossing each other. Okay? So let's talk about schematics a little bit and how we draw schematics. So if I have this, I got a battery and I have one resistor here and I have a capacitor here, and the capacitor crosses over and does that. This is a useless circuit. This does nothing useful, okay? But this is an example. I indicate the crossing without a connection by usually doing that, by showing a little loop, a little flyover, okay? So this little hoop indicates that there's crossing without contact. If I wanted to show contact, then I would just draw it like that. Okay? Or if I had another thing over here, I might draw it like that. Okay? In some textbooks, now this is the complication. In some textbooks, and these are fairly widely used, this is not an unusual thing. Unfortunately, a slightly different nomenclature is used, which makes life difficult. In a system where there is a crossing, let's say I have a resistor here and I have a capacitor here, if they are intended to touch, they'll put a dot. And if they are not intended to touch, they will just draw them crossing without a dot. Okay? The problem you see is there's a double usage. This looks kind of like this if I didn't have a dot here, right? So just be aware of it. The easy way to tell is look through your circuit. If you find elements that you know should not be touching and they don't have this, they just have straight lines, that means people are using that other nomenclature. Okay? It exists. It's reasonably common. There's no geographic. Unfortunately, I can't tell you English books always have this and German books always have this. It turns out this seems to be relatively widespread to see both. Okay. But at least for what we're doing here, if we have this little jump, that is clearly a situation where it is not a node. Okay? If there is a dot, it indicates that it is a node. It could be an ordinary node or an extraordinary node. It turns out we can define circuits based on how we can draw them. Most of the circuits that you're going to deal with are what we call planar circuits. Planar circuits are circuits that we could draw on a sheet of paper. So we could draw them in 2 dimensions without having to have branches crossing each other. Okay, so for example, this is a circuit. It looks like branches are crossing each other. But it turns out, of course, I can redraw it, and I can redraw it such that it is planar and does not have any branches crossing each other. Think about it. R4 is connected from one end of the source. It's connected from the negative of the source to the node between R1 and R2. Well, let's just take out R4 and connect it from the negative of the source to the node between R1 and R2. So, a planar circuit can always be redrawn without having crossing. The advantage is it makes analysis easier. It's easier for you to identify where the loops are, where the nodes are. It makes life easier. Yes, question?
Is it only theoretical insofar as drawing it? Because what you spoke before about the flash,
Yeah.
so can it cause any problems in the flow?
Oh, you mean the tunneling that I was talking about? Oh, these gaps are really far apart. So no. Look, pretend I never said anything about flash memory and tunneling, okay? That doesn't exist as far as you're concerned right now. Okay? When I draw this, don't worry about electrons jumping from here to here. That doesn't happen. Because these are not 2 nanometers apart. They're more than that. Okay? So yeah, it's not an issue. So this is the first rule now of analyzing circuits. We've got our first rule. Our first rule is make your life easier. Usually, try to redraw the circuit such that you don't have to deal with these weird things. It makes it easier for you to identify loops and so on and so forth. And so it's usually easier to start by just redrawing your circuits like this. Okay. We now get to introduce arguably the most important rule you're going to learn in this class. Or this is one of 2 really important rules you're going to learn in this class. And that is the law associated with the current entering and leaving a node called Kirchhoff's current law. Okay? And specifically, what the law says is the sum of all the currents entering a node is 0. Now, I've put it in a specific way. I've said the sum of all currents entering a node is 0, which means if currents are leaving a node, you treat them as negative. Another way to say that is whatever current goes into a node has to come out of the node. Okay? So that's another way to say it. In other words, if I were to write it mathematically, the sum, let's say I have n lines, n branches running into a node. And I'm going to use a model. I'm going to use a convention. My convention is going to be if the current goes into the node, it is positive. Okay? If the current goes out of the node, it is negative. I will say that the sum of all the individual branch currents is going to be equal to 0. Let's take this example here. In this example, I1 and I4 are going in, I2 and I3 are coming out. So I sum them. I1 is positive because it's going in. I4 is positive because it's going in. I2 and I3 are negative because they're going out. In other words, the sum of all of them is equal to 0. Okay? First law. Second, another way to state that is all the currents going in have to equal all the currents coming out. Okay? This law is a very important law, and it allows us to start doing analysis because we can take a system with ordinary nodes or extraordinary nodes and we can figure out the relative currents. Let's go back to this example. I know that the current coming in through R3 and R2 must equal the current going out of R5 in this case. Let's say current is coming in this way and current is coming in this way. The sum of these 2 currents must equal the current going out of here. So life starts getting easier. I can start simplifying. Question? So, again, tunneling doesn't exist in our class, right? So, actually, there's a more fundamental assumption than that. The more fundamental assumption is charge is not building up anywhere. Things are not time variant. Okay? It is, for these sorts of analysis, it's not, I mean, it's fundamentally true. You can assume it is true. No, it's not related. Remember, for any system that we have, I mean, think about it. You have a circuit in front of you. It's not like electrons are flying up into the air, right? They're running within the circuit. In fact, there's an infinitesimally small number of electrons flying out into the air, but they're tiny. So we can ignore those. Yeah. Okay? Yeah. Mm-hmm. Oh, yeah, you're making my life difficult. Okay. All right. So that's the first law. Now I get to use that law, and we often refer to it as KCL, okay, for Kirchhoff's current law or Kirchhoff's current loop calculations, and you'll see how we do it in a minute. Okay? Here's a circuit. The circuit I'm going to give you is shown right here. What is this source? Is it a constant current source or a constant voltage source? It's a current source because we indicate with an arrow, and in fact it says 10 amps. So I have 10 amps of current always coming out of this circuit. Excuse me. And it is going through this resistor, which is a 3 ohm resistor, and there's also another portion over here which has this resistor, a 1 ohm resistor, a 2 ohm resistor, a 10 volt source, and a 4 ohm resistor. Okay, let's write, excuse me, let's start writing some equations that we know. Okay, first, the first equation that we know is going to come from a calculation associated with I2. Okay? So I'm going to ask you to calculate I2. So let's start. For arbitrary reasons, I'm going to pick this resistor. And this resistor that I'm going to pick is the 4 ohm resistor. The voltage across that resistor I will call V4. I'm giving you that as a fact. That's how I'm starting. I'm picking this resistor, the 4 ohm resistor, and I'm going to call the voltage across it V4. Okay, that's the voltage across it. Now, I want to know what is the current going through that resistor. How do I do that math? Yeah, it's Ohm's law. V is equal to IR. Okay, so V is V4. R is 4 ohms. So I can write I2 is equal to V4 over 4. Now let's go back to the problem. Here's the problem that I'm giving you. If V4, the voltage across the 4 ohm resistor, is 8 volts, I want you to determine I1 and I2. Okay? So I2 is easy. I2 is V4 over 4. That's 8 over 4. That's equal to 2 amps. Okay? First part. Second part, I'm going to do the math, excuse me, at this node, node 1. Is that node an ordinary node or an extraordinary node? Extraordinary. How do you know it? 3 or more branches. It has 1, 2, 3 branches. Okay, so it's an extraordinary node. 3 branches. What does Kirchhoff's law tell us, the current law? Sum of all the currents going in has to be 0. Okay. We will agree. Currents going in, we will call positive. Currents going out, we will call negative. Okay. This current is going in. So we've got, at node 1, the current going in is 10 amps. I1, I've marked as coming out. I2, I've marked as coming out. So I've got 10 amps minus I1 minus I2 is equal to 0. Okay? I1 goes in. I apologize. 10 amps goes in. I1 and I2 come out. So 10 minus I1 minus I2 is equal to 0. So I've got 2 equations. I2 is equal to 2 amps. And 10 minus I1 minus I2 is equal to 0. What is I1? Well, it's 10 minus I2, which is 10 minus 2, 8 amps. So you see how the KCL allowed us to determine I1. I2 was easy. I2 was easy because we knew the voltage. So we just used Ohm's law. I1, we needed KCL. And that allowed us to get to a solution where we've calculated I1 and I2. Yes? Good question. I haven't talked about that yet, but let's go ahead and talk about that. I2, it's going through this 1 ohm resistor, right? Does it go through the 2 ohm resistor? Yes, because they're connected to each other. Think of it. This is a node right here. Current is going in, must come out. Okay? Does that same current, I2, go through the 10 volt voltage source? Yes, it has to. There's a node here. Current going in, must come out. So this is what we'll call current continuity. Whatever current goes in has to come out. So in this case, I2 does in fact go through the 10 volt source. Okay? For which one? The 2 ohm is 10 volts? This 2 ohms? The voltage across that is not 10 volts. Why do you say that's 10 volts? Let's think about it. Let's figure out what was wrong with that point. Okay. So why do you say the voltage across this is 10 volts? Sure, but the voltage is between, it's 10 volts between here and here. Right? Okay. So it's the voltage between here and here is 10 volts. The voltage between here and here is not 10 volts. Okay. I get to ask you a question. What is the voltage between here and here? 4. How do you know that? It's 2 ohms times I2. Because Ohm's law applies across that resistor as well. Okay? Yeah. Hmm? Actually, we are treating this as an ideal source. Okay? We're not modeling this as a resistor. What we have is I have an ideal source through which I'm forcing current through because I've got a higher voltage outside. Okay? So just treat it as that for now. Yeah, question. Good. So this is the same. This is actually, I think, related to the same question you're asking me. This circuit is somewhat confusing because normally I would say current should go this way, right? Yet I'm showing the current going in. Can anybody tell me why that is happening? I'm sorry? Yes, this current is so large that it generates a relatively high voltage across here. And so the voltage over here is actually larger than the voltage over here, which forces the current through there. Okay, tell me, what is the voltage across here? 24 volts. How do you know that? 3 ohms times 8 amps. So this is the answer. The reason the current goes in is because this source is stronger. And it essentially generates 24 volts. Well, 24 is more than 10. Voltages are all relative, so it's going to go in. Okay? Question?
Here, what's the voltage source even doing?
Well, in this case, well, you could argue, what is this circuit doing? The circuit is doing nothing. It's just burning power. Okay? No. But this was just to show you an example of a system that had 2 voltage sources and allowed you to look at the competition between them. This voltage source, really, if you were to ask what it does, it reduces I2. Because there's some voltage that's fighting against the higher voltage.
Did we factor it into our calculation?
Yeah, we did. We did sort of factor it into our calculations in the following sense. We factored it into our calculations because it turns out the fact that there is 8 volts across here only happens if this were a 10 volt source. If this 10 volt source were not there, let's say it was a 0 volt source, we would have a smaller, we would actually have a larger voltage across here. Okay? All right. So, running out of time, so we'll stop right here. We'll pick up on this in the next class.